Tonight marks a turning point. Only hours remain before 3I, Atlas, the peculiar emerald glowing wanderer from interstellar space, sweeps past Mars. What unfolds next could rewrite how we think about comets, visiting objects from beyond our solar system, and perhaps even our place in the wider universe. This is no simulation. The evidence gathered in the coming hours will either confirm months of speculation or fold the story back into the safe domain of dust and ice. From the start, this object has broken the mold. Unlike ordinary comets that drift into view with predictable brightening, 3I, Atlas has behaved erratically, its light rising and falling in sudden bursts far beyond what solar heating should cause. Spectrographs show carbon dioxide dominating its emissions where water normally leads the charge. Dust grains recorded by photometry teams are unusually large and slow, with sudden flares resembling deliberate thrusts more than natural jets. And then there is the color, a stubborn green halo that resists every conventional explanation. Individually, these details could be shrugged off. Together, they form a pattern that some researchers dare to call non-natural. Words like engineered and reconnaissance have crept into whispers. Now, with Mars directly in its path, those whispers are about to face reality. Earth will soon lose line of sight, leaving only Mars's orbiters and surface robots to serve as witnesses. MAVEN, TGO, Mars Express, and possibly even surface rovers, if weather and bandwidth allow, will be tasked with logging light, dust, and charged particles during the comet's passage. The mainstream interpretation remains conservative, an interstellar comet with an odd chemistry, rich in carbon dioxide and heavy grains. Buried reservoirs of volatile ices could explain the sporadic outbursts, and the emerald glow may be an exotic interaction of dust with solar radiation. These explanations are reasonable, and they will be tested first. But three stubborn anomalies continue to gnaw at the scientific community. The flight path. The comet travels unusually close to the plane of the planets, following a corridor-like trajectory suggestive of intent. The pulsed brightness. Instead of a smooth solar-driven curve, its light flickers in regular intervals, often tied to subtle accelerations. The strange chemistry. Anomalous carbon dioxide ratios and unexplained metallic spikes keep reappearing in independent observations. Tonight, scientists will watch for three decisive signatures. Fragmentation. Does the nucleus shatter under solar stress? A chaotic breakup suggests fragility, while a single massive flare would mean deep volatile reservoirs. Trajectory shifts. If the comet's path changes more than models predict, it could be asymmetric mass loss, or something harder to explain. Unexpected emissions. Radiation or particle lines outside natural cometary physics would force rapid rethinking. Mars offers a unique laboratory for this encounter. If fragments brush its thin atmosphere, they could spark temporary auroras or ionospheric disturbances detectable by MAVEN and TGO. Telemetry will be delayed by relays and solar interference, but the signals, dust composition, isotopic fingerprints, and particle counts, could be decisive. The stakes run deeper than orbital mechanics and spectral lines. If 3I, Atlas carries complex organics, long carbon chains, unusual macromolecules, or structures that mimic simple biological assemblies, those molecules may not remain aloft forever. Tiny fragments, dust grains, or vaporized material could settle on Martian soil or cling to the hardware that studies it. That possibility would complicate the work of future astrobiologists. Distinguishing a native Martian signature from an interstellar hitchhiker would become a matter of forensic science, not just more telescope time. Timetables for sample return missions, the wording of contamination controls, and the interpretation of past and future biosignature claims would all feel that ripple. Planetary protection is not an abstract policy in this moment, it becomes practical choreography. Teams will need to document when and where odd material was detected, preserve raw telemetry and unprocessed spectra, and maintain rigorous chain of custody records for any data or physical samples implicated in the encounter. Those records are the only way to later argue whether a curious molecule belongs to Mars, to a visitor from interstellar space, or to earthly contamination. At the same time, debates will flare about openness. Some mission groups argue for immediate, public release of all raw data to enable crowd-sourced verification. Others urge staged publication to protect sensitive instrument health data or national strategic interests. That tension between open science and operational prudence will be as consequential as any measurement tonight. Operational reality matters as much as the physics. The instruments positioned around Mars are diverse: imaging cameras, spectrometers that split light into its chemical fingerprints, magnetometers that map tiny magnetic disturbances, particle detectors that count ions and electrons, and dust analyzers that measure grain size and velocity. None of these instruments is perfect, and none is immune to a tricky calibration or a saturating signal. Telemetry must travel from surface assets and orbiters to relay satellites and then to Earth. Solar interference, limited bandwidth windows, and queued science downloads mean that the rawest, most decisive-looking packets will often arrive out of sequence or delayed. Teams will be working backwards: first triage, then verification, then interpretation. The global observing community, large facilities, small observatories, and backyard arrays, will function as a distributed sensor network. Amateur observers have long been the canaries in the coal mine for transient sky events. Tonight, a backyard spike in brightness may trigger a professional target of opportunity observation. That mixture of formal and informal observers increases redundancy and resilience, but it also raises challenges for quality control. Cross-calibration across instruments, independent reprocessing of raw frames, and simple common-sense checks, is that flash an instrumental artifact, a satellite glint, or real cometary activity, will be indispensable. 3 scenarios now dominate planning maps, and each has many shades within it. Conservative case 3I, Atlas behaves like a highly unusual but natural comet. It flares, perhaps sheds a few fragments, and survives perihelion before fading into interstellar night. The science payoff is enormous: new chemistry, fresh constraints on formation environments outside our system, and improved models of how heavy grains and carbon dioxide-rich bodies evolve under solar heating. The community publishes careful papers, updates models, and moves on. Only the chemistry textbooks gain new paragraphs. Intermediate case: the nucleus fractures significantly, producing a temporary debris field near Mars. The short-term hazard is micrometeoroid flux. Small, high-velocity grains strike delicate instruments, coat optics, or abrade solar panels. Some sensitive detectors might report increased noise or even sustained degradation. Operationally, teams may place at-risk instruments into safe modes, reorient spacecraft, or delay high-value observations until the debris clears. Scientifically, a set of fragments provides an unexpected bounty. Comparative fragment composition can reveal internal layering, volatile reservoirs, and mechanical strength. But it also forces mission managers to weigh the value of continuing observations against the risks to hardware. Extreme case: